we have following proposition. Corresponding to the decomposition of a space X into its path components into its path components X alpha, there is an isomorphism. There is an isomorphism of HNX with the direct sum alpha HN X alpha. So this is true for every proof. So if your singular and simplices are what? They are basically maps from here to here. So their maps means they are continuous functions from here to here. So this is what? This is simply path connected, right? This path connected. So continuous image of a path connected set is path connected, right? So this sigma alpha and this is path connected. Okay. So this is going to be belong to in a single path component, right? So if this is your X, right, and if you break it into its path components, suppose, then this is, if these are the path components of X, then this is going to, because this is path connected, right? So it is going to be completely either here or here or here, right? So it means what? It means that this CNX, right, you can break into uh, components, right? Since sigma alpha n is path connected for each sigma alpha, this C and X splits as the direct sum of its subgroups C and X alpha. So you just see here. So what is an element of CNX? See, elements of CNX, they are of the form n alpha sigma alpha. Okay, this is finite formal sum. Okay, So basically this will be of the forms n alpha 1 sigma alpha 1 plus n alpha r sigma alpha r, something like this. It will be like this. Now these sigma alpha 1 sigma alpha 2, they are, suppose they are in CNX. Okay. Now because this sigma alpha I delta n, right, this is completely, this is going to be inside a single path component of x, right? It means what? Suppose this is x is your xi, right? Suppose xi's are the path components of x, right? Okay, so here I am using the xj, right? Then because this is going to, so this is going to be in some xji, right? It means what? It means this is going to be an element of what? It is going to be an element of CNXJI. Okay. Similarly, next one, right? So ultimately, what we have, right, this is in uh, CNXJ, right? So this is direct sum of path means this CNX is, right? Because each term here is going to be in single CNXG, right? So every element here, you can write as uh, finite sum of elements in these CNXJs, right? It simply means that this is CNX is simply this direct sum of CNXJs. Now, this boundary map, uh, now this uh, from CNX, right, to Cn minus 1x. Uh, so if we look at this boundary map, then it will take this basically so this is your CNX alpha, suppose we use notation, right? This one x alpha. Okay. So this preserves this thing, right? It means what? It means that this preserves this direct sum decomposition. What does it mean? Uh, It means that if you take an element, this uh, uh, n alpha sigma alpha, sorry, use some other notation. So suppose ni sigma I in if we choose this in Cn x alpha, suppose, right? Then this applied over this summation, this will be in Cn minus 1 x alpha. Why it will be there? Just see what is it? What is it actually? This is summation ni sigma n sigma I, right? And this is what? This is basically just some of restriction of sigma i's, right? So this is what sigma n, sorry, boundary n, you know, if you recall, boundary n sigma, it is simply what? It is summation j between 0 to n minus 1 to the power j sigma restricted over p naught bj vn, right? So sigma restricted over faces, right? Boundary faces. But image of sigma, if this is here means what? Image of E sigma I belongs to x alpha, right? But then restriction of these sigma i's over the boundary faces also will go to x alpha, right? So these also, they also will be x alpha. That is each sigma I, each boundary n sigma I will be x alpha. It means that this is here. So this is meaning of preserving the direct sum decomposition. Uh, Hence, this Zn x it also splits into Zn Zn x alpha alpha and Bn x equal to Bn x alpha. This is what? This is just kernel boundary n. This is image boundary n plus 1. Okay. So because as a consequence of this, we have this. Now, therefore, we have Hnx equal to this Znx represented by Dnx, but this is what? This is Znx alpha represented by Dnx alpha this is going to be isomorphic to Zn x alpha represented by Bn x alpha. So here you should notice that because of this, here that I said, right, this if you bound the n applied over Cnx alpha, it is going to be Cn minus 1 x alpha. Okay. So because of this, we have Zn x alpha, right? This Bnx alpha will be contained in Znx alpha, right? So we can talk about this, right? So this is Hnx. So this you can verify. This you have to verify. So this one is an exercise for you to verify. Reason is following: if x is a non-empty and path connected, if x is non-empty and path connected is space, then zeroth homology group of x is isomorphic to Z. Hence, by using previous proposition, for any space x h naught x is a direct sum of this z, one for each path component of x, right? So we have seen that Hnx equal to Hnx. In particular, h, x to h0 alpha, but x alpha is path component. It means it is obviously path connected. So this for each alpha, this is z, right? So this is direct sum of some copies of z. So here number of copies of z will be the same as the number of path components of x. So proof. So by definition, we have h x equal to quotiented by 1, right? But this is what? This is your C0x quotiented by 1, right? Because this is 0. Because our chain complex is something like C1x, then C0x, and then we have 0, 0, 0, 0, right? So this will automatically be a 0 map, right? Now define a homomorphism is epsilon from C naught x to z by epsilon summation I sigma I equal to summation this, right? This is finite sum, right? So obviously these ni's are what? Ni's are integers. So this finite sum of integers is again integer, right? So yeah, this is well defined, and so clearly epsilon is surjective. So you can see that if you choose any, it is surjective if x is non-empty. Because if x is non-empty, then there is at least one 0 simplex, right? So suppose that is sigma, right? So for every n in Z, n sigma is an element of C naught x, right? And hence epsilon n sigma is what? It is simply n, right? So epsilon is surjective if x is non-empty. Hence, this C naught x quotiented by kernel epsilon is isomorphic to Z, right? So because epsilon is surjective homomorphism, so this quotiented by its kernel of epsilon is isomorphic to Z. Now, we shall prove that image boundary 1 is equal to actually kernel epsilon. Now, if we can prove it, then what our zeroth homology group was uh, it was this C naught x quotiented by image boundary 1, right? But if we can prove this, then this is nothing but C naught x quotiented by kernel epsilon, but this is actually Z, right? Hence this becomes Z. So if we can prove this, then we are done. Now, first we prove that image boundary 1 is contained in kernel epsilon, right? So for that, we can choose some element here. Okay. So for any uh, singular one simplex sigma here to x, we have uh, epsilon 1 sigma equal to so this standard one simplex, it will be of the form some your b naught b1 something like this. Okay, so if you apply boundary map, then we have here sigma restricted over b1 minus sigma restricted over v naught. Okay, that is how we define this boundary map. So when you remove v naught, so we have minus 1 to the power 0. When you remove v1, we have minus 1 to the power 1. So we have something like this. But this is what? This is a singular zero simplex. This is another singular zero simplex. And we have seen that epsilon applied over summation ni sigma I is nothing but summation ni, right? So this is this minus this, right? Epsilon applied over this minus this. What is its coefficient? It is 1, right? What is its coefficient? It is minus 1. So we have just 0. Okay. Hence, so this is for one singular one simplex. Hence, this epsilon applied over the one summation I sigma I equal to this is ni epsilon 1 I. This is 0. What is this? This is an element of C1 x. Okay. So because this is 0, so this is basically hence. So this is put image boundary 1 because every element in this will be of this form. Okay, and if you apply epsilon over this here, you are getting 0 means this is in kernel epsilon. So let us prove the converse. Okay. let sigma I epsilon, that is epsilon applied over summation I sigma I equal to so this is in kernel, means epsilon applied over this is 0, but this is by definition of epsilon, it is this. So this summation ni is 0. Now so this sigma is our what? Sigma I is here, they are singular zero simplices. So we can consider them to be maps from sigma, they are maps from 0 to x. But this, we can consider this to be simply this. Okay. So standard zero simplex is simply a single point. Now, so here we define choose a so x is path connected. We have chosen x is path connected. So here we can since x is path connected, choose paths tau I from tau I from 0, 1 to x such that tau I 0 is x naught and tau I 1 is this is your sigma I v naught. So in fact, we can consider them to be from. So what is this basically? This will be a something standard one simplex. So we can consider the vertices of uh, we can consider vertices of these to be we will match with this. So we need to. So maybe we can take 0 and 1. There is no problem if we take 0 and 1. So and we consider sigma naught to be let sigma naught be a 0 simplex be a singular 0 simplex such that sigma naught uh, this equal to x naught. Now let us see what happens. So I think if we consider here tau y from v0 to v1, it will be convenient for us. We can always do it, right? v0 comma v1. Okay. So always we can do this because for any v0 and v1, of course, there is a homeomorphism between these and 0, 1. So we can always have, if we can have a continuous map from 0, 1 to x with this property, then we can have a continuous map from. So this is going to be tau y v naught. So we want it to be v naught, and this one we want to be v1. Such that this is your this we can take. Now boundary map, if you apply tau I equal to tau I restricted over v1 minus tau I restricted over v0. Now tau I restricted over v1, you see here, it will give this sigma I, right? So this is sigma I, and this is uh, sigma naught. So here you should notice that yeah, so tau I restricted over V1 is actually a singular zero simplex, right? And uh, this is exactly equal to sigma I, because tau I applied over V1 is simply sigma I applied over V0. So sigma is a singular zero simplex. So this is going to be equal to this, and this tau I applied over V0 is actually equal to x naught, and sigma naught is a zero simplex such that here so I think it will work even if I write sigma 0 here and sigma 0 here, then there will not be any confusion. And because we are already taking this, now what we have here, hence if we apply this over summation I tau I, then this is going to be summation I, so tau I goes to this sigma I minus summation 0. This is summation I, 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 and because this summation sigma I, summation ni, this is 0, already we have seen. So this is going to be 0, and we are getting this summation I is 0. So what we have is, so we have that this is an element of the kernel, and it is boundary of, so hence, so this summation ni sigma I belongs to boundary of image, sorry, this belongs to image of boundary point. So this completes the proof, because we have taken an element in kernel and we have shown it is in the image boundary 1. Then kernel epsilon is in image boundary 1. So here it is important to identify the things. Uh, So what actually we have, if we have this x is this one, right? And we have this summation ni sigma I. Then these ni sigma is are zero simplices, singular zero simplices. So their images will be somewhere here, here, like this, right? So we can call them sigma I v naught, sigma 1 v naught, sigma 2 v naught, something like that, sigma I v naught. And we can choose a point x naught, right? And we can always find a path because x is path connected from here to here, similarly from here to here, and then from here to here, like this. And these paths, we can view these paths uh, uh, as images of singular one simplices uh, to x, right? We can always view them. So this is so similarly, yeah, yes. So what happens that we can consider a singular zero simplex whose sigma naught, right? This is sigma naught uh, v naught. Okay. So we can additionally we can consider a singular zero simplex whose image is x naught. Now, if you apply these boundary maps over this tau I, then this is tau I restricted over. So this is this one. Uh, so your standard one simplex is basically what? It is basically uh, so this is point E0, sorry, E1, and this is point E2, then it is just, okay. And your standard uh, zero simplex is going to be, so this is uh, so E1 you can treat as V naught, this you can treat as V1. So this one is going to be your standard one simplex, right? So obviously one vertex of this is going to be the standard zero simplex. So that is why we have like this. So this restricted over V1 minus this restricted over V naught, right? But this is what tau I restricted over V1. This is equivalent because tau I is from where to where? From here to here, right? So tau I restricted over V1, this is a zero simplex whose image is going to be this. So, but that zero singular zero simplex is nothing but sigma I, and this one is going to be sigma 0. So similar. So if we once we have this, one can talk about image of this I tau I, and then one have this 0.